All right. So what I'm going to do here is I'm going to introduce a couple of concepts here that are really important to us in terms of electric circuits. And that is the idea of loops and junctions. We'll start with loops. So let's say that we have a power supply and and it's connected up to a resistor. We know that current's going to flow right there. Okay, and so what's going to happen is we know that V equals IR. Well, that V is the EMF right there. So but we also know that this side's positive, that side's positive, negative current flows that way. All right, so let's expand this. Let's say that we have a power supply here. We have another power supply there. Okay, we come up here. We have a resistor. We have a power supply there. We have a resistor, okay, and we have another resistor right here. And so we can call this EMF 1, EMF 2, EMF 3, R1, R2, R3. Okay, so this is the negative and positive side of that. This is the negative and positive side of that. This is the negative and positive side of that. Now, we have to make an assumption as to which way current is flowing. So current can flow clockwise or counterclockwise in our loop. So we're going to assume that current is flowing clockwise. You could have done counterclockwise. That would have been just fine. Now, what I'm going to do is I'm going to start a loop somewhere at any place right here, and I'm going to go around, and it doesn't really matter where I'm going. Now, when I go, if I were to go clockwise from my starting point right there, then I will pass by this EMF first and then this EMF second. And so what happens is I'm going from negative to positive across the EMF, so I am increasing potential. So that's EMF 1 plus EMF 2. Now, if current is flowing this way, clockwise, we know it goes from plus to minus through a resistor. So it goes plus, minus, plus, minus. So that means when my current goes across this resistor going plus to minus, it's losing voltage. So there's a voltage here. V1 is going to be IR1. So it loses minus IR1. Okay. Likewise, it's losing there too. You know, this V2 is IR2. This V3 is IR3. But I also have to pass by this second EMF, the third EMF rather. And I'm going from plus to minus, so I'm actually decreasing because it's fighting against me. Okay, minus IR2 minus IR3, and I'm back at the beginning, and the difference between beginning and end is 0. So if I'm back at the same spot, the potential energy is the same as it was originally, and so the potential difference is 0. What that means is if I take the sum of all the voltages in a loop, it adds up to 0 for a closed loop. This is what we call the loop rule. Now, turns out that by using this concept right here, I can actually learn a lot about how circuits operate and how batteries work. And so we'll be getting back to that. But first off, we got to introduce the loop rule. So the sum of the voltage around a loop is 0. Okay. Likewise, if I have a power supply and I have like multiple resistors, we have an EMF right here. We got current flowing, so we call that like I1. Okay, when it reaches this junction, some of the current goes through that resistor, R1. Some of this goes to the other one, R2. So this current on the left I'll call I3, and the current on the right is R2, just because I feel like it. Okay, so what happens at the junction here is current into the junction has to equal the current out of the junction. That's conservation of charge. So I1 has to equal I3 plus I2. Now, at the other junction, I have I3 going in, I2 coming out. If this is I1 going up this way, that has to be I1 right there in order for conservation of current. So that means that this is I1 right there. So current going into that last one is I3 plus I2. Current coming out is I1. I can summarize the junction rule is that if I have a junction here and I have currents here, okay, so I could have this, you know, so that I can have multiple currents coming out. So this is going in, these are going out, and so what happens is that I would define current in. The sum of the current in equals the sum of the current out. Do an example. Let's say that we have a power supply right here, and we've got like that, okay, and then this comes together, and then what happens is it splits into 3, and we got 3 more resistors right there, and then they come back together and then off this way. And so what would happen is we've got a current here, and call that I1, and right here we have I2 and we have I3. So that junction right there tells me that I1 plus I1 is the current going into that junction. That's equal to I2 plus I3. Now for this junction right here, I've got I2 and I3 going into there, but now it's splitting into I4, I5, and I6. So that means I2 plus I3 equals I4 plus I5 plus I6. At this junction right here, this has to be I1 for conservation of charge. So I4 plus I5 plus I6 equals I1. All right. So this is your application of that junction rule. Let me point out something very important right here. Okay. I could have 2 power supplies connected to a resistor. So that means I might have I1 here, I might have I2 there, and I might have I3 right there. So what would the junction rule look like? Well, the current in is I1 plus I2. The current out is I3. Okay, a common mistake that students make when they're doing this is when they're trying to solve these problems, because we're going to have to end up with systems of equations eventually, they tend to always write down I1 plus I2 equals I3, and that is sometimes not right. For example, in the previous example, that was not the correct expression. It is always, however, current in to the junction equals current out of the junction. This is always the correct expression, no matter how you label the individual currents. So if you keep that straight, it will save you some issues later on.